I'm Yi Bo, and today my topic is SPDK CSI to bring SPDK to Kubernetes storage. So recently we started the SPDK CSI project. So what it does is to make the workloads, containerized workloads in the Kubernetes can use the SPDK as the storage backend. So, okay, so I'm here to introduce the project and the concepts and some ideas of how it works. So first about me, I'm a principal engineer from ARM, and I have 20 years experience in software development. I'm currently working on improving open source software ecosystems on ARM servers, because ARM is also an important player in the server field, and have been big progress recently. My focused area is storage and data science. So for storage, especially the cloud storage and containerized storage. So this is the agenda. First, I will give an overview of SPDK and Kubernetes storages. So what is SPDK and what is the Kubernetes storage? Some basic concepts. And then I will focus on the container storage interface, or CSI. So the CSI internals. So why we need a CSI and how it works internally. And then I will give the introduction of Kubernetes CSI support. So how we can develop a CSI in Kubernetes environment. And then I will introduce the SPDK CSI implementation details. Finally, I will give the community, so the SPDK CSI community, how it works, and welcome contributions, and the project status and plans. I'll first introduce the SPDK and the Kubernetes storage. So first, what is the SPDK? So this is I quoted from the SPDK website. So the SPDK means Storage Performance Development Kit. So it provides a set of tools and libraries for writing high performance, scalable, usable storage applications. So the important things first is the high performance, then scalable and usable. So traditionally storage applications are based on kernel-based kernel-based storage stacks. So, but for modern hardwares such as the NVMe, the speed is very fast, and the CPUs have many cores. So the latencies and the bandwidths comes from the software needs to be changed to leverage these new hardware features. So SPDK is designed for this kind of new hardwares. So the key technology is first it interacts with hardware directory user space. It bypasses the kernels. The application directory access the hardwares, the storage hardwares. And it uses polling methods, do not use the interrupt-based. Traditionally, we will use interrupt-based, so the kernel will interrupt. We'll have a hardware interrupt the kernel when it finishes the package sending. But with pollings in the user mode directory, will reduce latencies. And there's no locks in IO paths. So what it means is that because there are currently multi-core CPUs, locks actually prevents the application's scalability. So with no locks, each IO path is independent. So it accesses their dedicated hardware queues. So it will become very high efficient. So this is SPDK architecture. So basically you can see there are 4 layers. The lowest layer is the driver, NVMe devices mostly. And then above this is block storage provider. So provided the driver accesses and to the above layers, to the above block storage service layers. So for the applications, the most interesting things comes from block storage services. So these layers will provide partitioning such as logical volumes, or cachings, poolings, or crypto compression. All these things are exported to the application as a block device, just similar to the traditional block device exposed by the kernel. But this device is exposed by the user space SPDK protocol stack. So for logical volumes, we can use it just like traditional volumes. So above this is the block storage protocols. So because we do not want to only use the SPDK in a single host, we want to in a network environment. So the applications in other node can access the SPDK storages in another node through the network, high-speed networks, like NVMe or Fabric or SCSI. So this is what the block storage protocols are used for. Actually, this is especially useful in our in container cloud. So we want to use SPDK storages for the containers, inside the container cloud. And this is a must. The container nodes must connect to the SPDK node through the network. Okay, so this is some further introduce about network storages. Yeah, so for network storage protocols, SPDK implements NVMe or Fabric and SCSI. And for volume management SPDK logical volumes provide flexible block devices interface, just like traditional kernel provided logical volumes. And then the remote configuration, because the logical volumes we want to create it and delete it dynamically. So we need a remote configuration interfaces. So for SPDK supports JSON RPC based remote configurations. So the client can send the JSON RPC commands to the SPDK target to create volumes, delete volumes, or to export NVMe over Fabric or SCSI targets to configure the internals of how SPDK works. So this is also very important for our SPDK CSI to work. Okay, this is a picture of what I just said, SPDK in the network. So this part, this block is the SPDK node. We have 3 levels of protocols, protocol stacks inside the SPDK node, the device level and the service and the protocol. Protocol is exported through the NVMe over Fabric target. And this is the client. The client want to use the NVMe, want to use the storage services through the network. So actually there are 2 networks in between the client and the SPDK node. First is the control network, because I just said we need to configure the SPDK to let it create volumes and let it export some disease volumes to some port or to some target, target port. So this is what the control network does. It sends JSON RPC to the SPDK JSON RPC module. Then it will create and delete and configure internally SPDK nodes. After that, the client need a data network to connect to access the high speed storage services. So normally this can be RDMA or TCP based or NVMe based on RDMA or based on TCP or maybe SCSI. So since this kind of data networks. So this is how the whole thing works. Okay, this is for SPDKs, and I will introduce the Kubernetes storages. Kubernetes has volume drivers to integrate third-party storage providers into the Kubernetes. So in history, for first version, in-tree devices, in-tree source code are implemented at the very beginning. But this will couple the storage provider's code to the Kubernetes source code. This is not good. So this is already deprecated, and the legacy code will be removed. Then flex volume is designed. This is actually a executable based API, binary API. So the application levels. So not the source code levels API. So this is very hard to deploy, and dependencies hard to management. So the state-of-art method of integrating storage third parties storage drivers is used the container storage interface, or CSI. So this is the emphasis. I will introduce deeper how CSI works in later slides. So for Kubernetes storage, the most important thing is the dynamic volume management. So what it means is that if a workload want to need some volumes, some volume sizes, some size volumes, it needn't know where the volume is and know how the volume can be attached to me. So this is these details should be left to the Kubernetes and to the storage plugins. So for the pod, so what it requires is just it says I need some. For example, I need 1 gigabytes of SPDK based storage. So this is the concept of the persistent volume claim. So for the application, it just claims some storage with some properties. Then the storage and the CSI drivers and the Kubernetes will create the appropriate persistent volumes and from the storage classes. So what it means is storage class is related to a CSI driver, and the persistent volume is related to the actual storage devices that is created by the storage driver. So this is how the dynamic volume management, the concepts of these keywords. So this picture is maybe easier to understand what I just said. So you can see the upper this line, the upper half is the Kubernetes cluster, and the lower the bottom is a storage provider. Storage provider may be some cloud storage provider or Ceph cluster or our SPDK cluster. So for the this is a pod. So is the workload. You can see this is a pod that it wanted to use storage provided by this storage provider. So how it can achieve this goal? So first it will create a PVC, a persistent volume claim. Persistent volume claims in the spec, it will request some resources. It says that storage 1 gigabytes and the storage class MySC. So what it means is that I need 1 gigabyte storage from the storage class, or the storage provided by this storage class. Since this storage class, it has a provisioned means named my CSI driver. So this driver is linked to the actual CSI drivers that is providing the storage to this storage class. So when the pod starts, in its spec, it creates persistent volume claims with this name. And the persistent volume claims linked to the storage class. So the storage class will find the actual controller CSI drivers. So the CSI drivers is responsible for creating the necessary devices through the whatever API is necessary. So if the storage is provided by Ceph, it will implement the Ceph API. If my cloud, some cloud API, SPDK, use SPDK API, things like this. So after it's created, there needs some way to mount that remote block device to the pod. So this is what the CSI node driver does. So CSI node driver will be notified when the CSI controller driver already created volume. It will receive a message that we needed to, the volume is created, I needed to mount it to my host. So what it does is to mount the created block devices to local host, then send to the host, and find it to the pod. So the pod will have access to the devices, to the storages provided by the cloud. So this is how the whole process works. So for SPDK CSI, this is our new project. This brings the SPDK to Kubernetes. So the goals of this project is to bring SPDK to Kubernetes through NVMe and iSCSI, and support dynamic volume provisioning, and enable pods to use SPDK for transient or persistent storages. And non-goals with this not a complete storage solution. So this only creates block devices and file system accesses to the remote block, but this is not a complete storage solution. And the SPDK node management is out of the scope. Okay, so now I am give some deep introduction about the container storage interface. So container storage interface from the CSI spec, it says it has formal definitions, but I find this is not very easy to understand. From my point of view, actually, the CSI, what the CSI does, it defines a bunch of messages, or RPC messages between CO. CO means the container orchestrator or Kubernetes, and third-party drivers. And it also defines volume life cycle management based on these messages. So basically, it's a bunch of messages and how the system should work under these messages. This is what CSI does. The focus on the volume life management. Here I'm listed an example. So to see why CSI is needed and how is it useful in the actual space. For example, I want to use block devices in a containerized app. So first, when the app starts, it needed to create the Ceph volumes in the Ceph cluster through the Ceph API. Yeah, so this is the first step. This can be run on any host that can access the Ceph and with the necessary tokens maybe. So this is one step. Another step is that after it's created, it needed to some method to mount the remote block device into local device. Mount the remote volume into local device, then mount the local device, local directory into the pod, into the container, inside the container. So this is what the steps 2 and 3 does. These steps must be run on the host where the actual application is runs, actual container is runs. So this is two different kind of requirements. In CSI terms, the first step, what we need is a storage driver to handle Ceph API and create a delete RBD on demand. It can run on any host which have access to Ceph cluster control planes. It only needed the control planes. It doesn't need the data plane. So this is in CSI terms, the CSI controller driver. So CSI have a controller driver to do this kind of control plane handlings. And for other 2 steps, it will need a storage driver to mount and unmount the remote Ceph RBD volumes to local host. And it must run on the node where the container is actually scheduled. So this in CSI terms is a node driver. So what it means is that the node responsible, the runs on the node where the application is runs. So in CSI terms, node driver. And between these drivers, there's a bunch of messages. We need a protocol to define messages between the container orchestrator and the plugins and these two drivers, so they can cooperate to finish the job. So this is the RPC and the volume lifecycle management. So this is what the core things that the CSI driver does. Okay, so I just said a controller driver and a node driver. So you can see this is a CO or a container orchestrator or master node. Then it has some, it can have controller driver run on any node, maybe master, maybe worker, every node is okay. But for node drivers, there must be only one instance running on each worker node. And they all connected to the CO, so it can communicate through the CSI defined RPC. This is how everything combined together. Okay, so for CSI RPC messages, I list some key messages that is most used. First is the to CO to the controller driver to have create a volume, delete a volume. So this is easy to understand, and also a controller publish volume, unpublished volume. And what it does is expose the volume to be accessible from the work node. So actually, in most cases, we don't need these two messages. It is used for some storage providers. For most use cases, create delete volume is okay. And for CO2 node driver, it sends messages like node stage volume and publish volume. A node stage volume means to mount the remote block device into the local stage host, stage node, stage directory. So the publish volume mounted bind mount the stage directory into the directory inside the container. So we need two steps because there may be two containers run in a same node that shares the volumes. So we have these two levels mount passes to make it easier to handle. So this is the picture from the spec of the CSI spec volume life cycles. So first the create volume becomes created, then controller publish volume message received, and then become node ready. So ready for mount by node. So node stage volume, actually node, this is mounted by the node and becomes volume ready. After node publish volume, it's available inside the container, so becomes published. And this is the reverse path. So for Kubernetes CSI, because CSI is a general protocol, it supports Kubernetes or other COs like Mesos. But if Kubernetes has a good support for CSI. Actually, I listed here some common practice in developing a CSI in Kubernetes. First is to wrap controller and node driver in a single binary. So because we see there are controller drivers and node drivers, this is not necessary be separate binary. They can combine in one binary to share some code. Just use the startup parameters to differentiate to make it behave different by the command line parameters. And to deploy controller driver as a deployment stateful set, and deploy node driver as daemon set, because daemon set has exactly one instance for each work node. So this is a perfect fit for node driver. And to leverage CSI sidecar containers to reduce boilerplate code. So I will introduce it in next slides. So sidecar containers, because Kubernetes has, for CSI driver needed to communicate with the API server. So it has many similar codes for each CSI driver. So each CSI driver all have to do this kind of things. And the contacting the CSI driver, connecting to the API server is non-trivial. It has large numbers of code and dependencies. So to free CSI driver from talking directly to API server, so the Kubernetes community developed some sidecar containers like external provisioner, external attacher, node driver registrar. So to makes the development CSI driver much easier. So to focus on the interesting parts, not some boilerplate code. this picture should be clear about this concept. So for this is a CSI controller pod. The controller board, there are 3 containers in this pod. First is the CSI controller driver. This is what we need to develop. And there are 2 sidecar containers, external provisioner, external attacher. They are provided by Kubernetes community. So actually they are talk to the API servers, watch this persistent volume claim object and the volume attachment object, watch these changes. And if for the provisioner driver, if it watches there's a new persistent volume claim, it will send create volume, delete volume messages to the CSI driver, to actual CSI controller driver through Unix socket. Similar for this external attacher. So this CSI driver as a controller driver are decoupled from the API server. So it makes it much easier to develop and maintain. A similar idea for the CSI node driver. Driver register is at the driver startup time, it registers the node driver to the Kubernete. So the Kubernete, so this kind of messages will be sent directly to the node driver after the registration, also through Unix socket. Okay, so now I am introducing the SPDK CSI. So this is what we developed, so this is the overall picture of how SPDK CSI works. So you can see there are 3 parts. So the left part is the Kubernetes node. In the Kubernetes node, we have a Kubernetes cluster. We have 3 nodes. First is CSI, the work node, 2 work nodes and 1 master node. So in one work node, we have a CSI node pod and a work pod. And in one node, we have a CSI controller pod. And this on the right side, this is the storage node. Storage node, so some hosts with NVMe devices and running SPDK stacks above it. In the middle is the network connections. So for network connection, you can see there are 2 networks. First is the control network. Control network is only the CSI controller driver can access this control network. It can send commands, JSON RPC commands to the SPDK node, one or any of the SPDK node storage nodes. And the node driver, SPDK node workers that runs the node drivers will have access to the RDMA, to the network, data plane network through RDMA or through TCP or maybe FC. And anyway, so this is the high-speed data network that connects directly to the work pod. So this API server as the center to control how things are work together. So this is we just combined everything together about this. So to repeat what I just said, so these tools are the external provision and external attacher, and this is driver register is provided by Kubernetes community as the sidecar containers. So we only needed to develop these 2 drivers. So these 2 drivers actually didn't contact the API server directly. Controller drivers, it contacts to the control plane of the SPDK node. But for node drivers, it contacts directly to the data path to the SPDK node. So the NVMe target or SCSI target like this. Okay. Sorry. This is what the SPDK CSI controller driver internally works. So basically it translate the CSI messages to the appropriate JSON RPC messages. So we can see in a simple way, we can see what CSI driver does is this. Controller configures the SPDK network target through JSON RPC. So for example, if the controller receives a create a volume message, what it does is it sends the BDEV viewer creator. This is create a logical volume. This is a JSON RPC defined by SPDK to create a logical volume inside the SPDK node. So the CSI controller driver will send this message to the SPDK node. For delete volume, you just delete it. For controller or publish volume, unpublished volume, it will send JSON RPC to the SPDK node to something like NVM subsystem at NS to add the network at the NVM namespaces or add the listeners. For iSCSI, the create a port, create initial port groups like this, and create a target node. So all this is necessary steps to make the outside to connect to the network target in VMF or SCSI network target. So this is done in the published volumes. For CSI node driver, node driver needed to connect to SPDK target and mount remote volumes. So basically, node driver, what it does is similar to the iSCSI or net or NVMe fabric initiators. What it does is to connect to the data paths of the connect to the target exported by the SPDK network target protocols. So you can see as for CSI messaging, if the node driver receives the stage volumes, what it does is runs NVMe connect, NVMe command line, connect some NQN, the target IP, target port like this. So to run this command. So this is a standard NVMe command line initiate command lines. So what it does is to connect to the remote target and create the local block devices related to the remote target. And after it's created, it will mount the imported device to a staging path, to a local path. And then for unstaging, I just do the disconnect NQN. And for published volumes, what it does is so we have already mounted the remote device into a local stage path. Then you can bind mount the stage path to the pod, to the path inside the pod. So this is what published and unpublished does. For iSCSI, actually simulate use iSCSI admin iSCSI tools to connect to the IQN and some port discover like this, similar to just what we did in the command line, but this is did inside the node driver in automatically. No need to manual configurations. Yeah, but you can see there are some parameters I marked red. So NQN, IP port, like this. This messages where the node driver knows these messages. So actually, these messages are sent from the controller driver because controller driver knows what the NQN is, what the node storage node IP and the port is. So these messages will be packed in a map, in a string-to-string map, and the controller driver will send it to the API server, and the API server will forward it to the node driver. So when the node driver is ready, it will get these messages and get these correct messages. So to get all these messages, so to connect it to the correct target. So CSI driver already defined all these message passings. Okay, this is the sequence diagram. So actually, it should be clear now how everything works together. This is the sequence of create and attach volume. So for a client want to deploy some app with some storage requirement. So first, you kube control some file, apply some file, but the YAML file is received by the Kubernetes, and inside it will find what it needs, the process volume claims, and so the controller driver will receive the create a volume RPC, CSI RPC. So controller driver will send JSON RPC to the storage node. So this is the storage node, SPDK storage node. After the SPDK receives this, for example, PDAV volume create, it will internally it will create logical volumes of the appropriate size and create an MVAF subsystems if necessary, then return the response. If everything's okay, then the API master, Kubernetes CO master will also secondary will send the controller publish volume. Controller publish volume, then the CSI driver receives this and translate it to the JSON RPC, NVMF subsystem at the listener to the SPDK node. So SPDK node will do the appropriate things inside to make the logical volumes accessible from the outside through some specific port or NQN names. So this is what the controller driver does. Controller driver, if everything is okay, the controller driver, then the node driver will receive the node stage volume request. Then this is the node driver. So what the node driver does is running the NVMe command lines, initiator command lines to connect to the target, remote target, and connect to the NQN IP port like this, and mount the device, import device and mount devices to the local stage path. Then the node publish volume message, when to receive this, it is simply bind mount the staging path to inside the pod, so the pod can have access to the storages. This is done. And this is the teardown. So this is create and attach volume. This is what the deleted because the client deleted the app. So this is similar, just a reverse. First, the node driver will unmount the volumes and unmount and delete the local directories, and then the controller will send a message to delete the logical volumes inside the SPDK node. So new clients can reuse this deleted node. So this is how everything works. Okay, so I'm also here. So this is SP development, but also deployment is also very important thing. Because in the cloud environment, so deployment is also a big headache. It's very hard to get it work correctly and robustly. For development purpose, we use Minikube as only for development purpose. So it is very convenient to deploy and test node driver, CSI drivers inside a single node. And because besides the Kubernetes cluster, we also need a SPDK service. So we want to access service from SPDK. So there's currently no automatic way to do this. We provided some scripts to build a SPDK container and container image and start it run with some commands. And next, we need to deploy SPDK CSI components. So the CSI controller driver, node driver, storage class, and some RBAC access control, and then many things. So all these things need to be correctly write into the YAML files and to deploy it. And after everything is deployed, we need to validate the SPDK CSI driver works. So the normal, the standard way to to test the third-party CSI driver is to use end-to-end test. So end-to-end test, what it means is it works just like in the real world environment. You deploy something and you inspect the internal status of every object, Kubernetes object, to make sure that you achieve the goals what you expected. So there's too many details, many details in this, so I'm not to list everything here. So if you're interested, you can see the source code. All these scripts, YAML files, and the E2E drivers are already implemented in the source code. And we have a CI system, so you can check the CI related scripts to see how everything is worked, how the deployment works. And here is some tips about the developing a CSI driver. First is about idempotency and concurrency. So idempotency means that because we are in distributed environment, so the messages may come out of order or may come duplicated. What it means that, for example, you received a create volume request and you created the proper volume, then you send a response back, but the response is lost or timed out or whatever. Just the sender didn't receive the response, so to send again the create volume request, the same request. So if you didn't handle it correctly, then you will create two volumes of same. So there may be some troubles, cause some troubles. So this kind of things. Another thing is the message may be out of order. So for example, normally we want to tear down a volume. The first the API server will first send unpublished volumes and send a deleted volume. But sometimes unpublished volume will comes after deleted volume. So if you didn't handle it correctly, then you maybe cause some troubles in the source in the code, the logic or some things like this. So needed to be careful about this kind of things. And another thing is to take care of concurrency. So it's possible that some, for example, deleted volumes may come, two deleted volumes to the same node may come concurrent at the same time. Actually, I didn't see this in the real world, but I guess it may happen. So we have some unit test to test this kind of scenarios to take care of concurrencies. Out of order and the repeated message, I observed it many times in the real world application. Another thing is to keep the code simple. Keep the code simple and stupid, maybe. So what it means is to, for example, if you want to handle errors, do not handle errors. Just return. If you've met with some error, just return. Fail the code path. Then the Kubernetes will try again at exponential backoff time gaps. So if you try to handle errors and repeat and retries inside your code, it will only make the whole code much harder to debug. Yeah, just let the Kubernetes to handle the error retries. And another way is to suppress controller published unpublished volumes. So I just said that this message actually can be combined with the create volume and delete volume message in most use cases. So we combined this, and we have too few messages handled, so it will make make things much easier to handle, and the error is also much fewer. Okay, now the community. So SPDK CSI is in the SPDK community. So code review is at the SPDK Garrett. I clone this, and this is a GitHub mirror, and also the development guidelines, so how to set up the Garrett, how to contribute like this or in there. And there's a Trello board. The Trello board records the to-dos and the backlogs and and the project status in the Trello board. So welcome to use this project, and to maybe contribution is also very welcomed. So for the project status, current status is still alpha state. So the mandatory CSI functionalities are ready. So basically that means that it's workable. So you can, we have a CI system to validate that everything just works. So mandatory CSI functionalities are good. But this is not at the production level quality. No, this is and not achieved this. So that the plans is to achieve the production level quality by adding more tests and more improvements. Also, we have planned some new features, and this is in the Trello board. You can see this and welcome contributions. Another interesting thing is we are thinking about integrate with the Rock project. So Rock is the Kubernetes container orchestrator. So with Rock, if we integrate with Rock, so we will reach total solutions. Means for the SPDK cluster management also can integrate it into the or can be integrated. So it means total solutions to make leveraging SPDK to Kubernetes much easier. Yeah. So this is the references, some container specs, CSI documents, JSON RPC, and the CSI design document. Okay, so that's it. Thank you.